let's get started here. Oh, wow, there's sound coming out of there. All right. Switch it off. It's switched on. In theory, can you hear it? Oh, okay, so this is just for the video. Okay, all right. It's weird, I get an echo when well, whatever. All right, let's get started. I guess I got to click on the slide. There we go. All right, well, let's just start with some basic physics stuff here. So there's a lot of folks talk about the end of Moore's law. I always caution people about that because it affects the stock price of our foundries. They hate that. But it's also the case that things are continuing to shrink. They are, and I'll show you a chart later, that we are continuing to double the number of transistors every 2 years or so. The real problem that we're facing is that not everything gets better when you make it smaller. And so this is the case in point here. We've got a transistor. Now this is a planar transistor. We do FinFETs now, but it's the same, same thing. Power is voltage squared times the frequency times the capacitance. And when you make this thing smaller, capacitance goes down and it gets more energy efficient. And now we lost this V squared term. We can't lower the voltage anymore, so that becomes a constant. And that's the reason why we can't exponentially increase the clock rates anymore. But that capacitance, when this thing gets smaller, it does get better. The problem is the wires. The wires, when you get it smaller, the length will shrink, cross-section area shrinks, but the power does not shrink. The wires don't get better when you make them smaller because the resistance goes up when you make it smaller. And that's the fundamental problem. My colleague Shaker Borkar, when we were doing the exascale run-up, took a Pentium Pro Core and ran it through synthesis at a number of different technology generations. And at the time, they could only extrapolate out to 7. And you can see the amount of on-die interconnect power. So the interconnect is the on-die wires, basically. The wire power is already at about 16 times more power than is consumed by all the transistors that are on the chip. And so this is why, and I'll come back to this later, why I keep on saying ALUs don't matter. The transistors almost don't matter but for their need to drive the wires. And so this has changed the way that I think about chips and chip design, is the fact that the ALUs are almost free, but the wires that connect them together is where all the energy is going. At the same time as Shakar, this is like 2009, I did a similar diagram. All of these values are read off of the ITRS roadmap. People ask me why I stopped at 2018, because they quit publishing the ITRS roadmap in 2015. So I couldn't read these things off, and they're all proprietary now. But the point of this, you're going from left to right to left here, that as you move from the cross system to the off-chip DRAM, and you move closer to the ALUs, it used to be that our calculation, this blue curve is 45 nanometers, which was contemporary in 2008, that we spent a lot more energy on the ALU, and this is an exponential scale, than he spent moving the data around. But by the time we got to 11 nanometers, it was about the same amount of power to move data just 1 millimeter across the chip. And now we've moved to 7 nanometer, and now you're spending 16 times more power to move the data to the ALU than the actual cost of the ALU itself. And it's actually worse than that. This is from NVIDIA, but Gordon Keeler used it for his photonics program. This is the amount of power that goes to the IOs to move data on and off the chip. And it's almost matching at parity with the total amount of power consumed by the chip itself. And so data movement off the chip is really killer. Now the good news is you can dial down the speed at which you move stuff on and off the chip, but that's a problem for we always want bandwidth, and that's why it gets curtailed. And it's not a technological thing, it's where do you want to put your power in order to melt the chip thing. So the other thing that's happening, yeah. That's what we end up doing. So you end up curtailing bandwidth by lowering the frequency that you operate the interfaces. That saves you power, but curtails your bandwidth. So it's a constant trade-off. Where do I want to shift the power? Yeah. It is done dynamically. This is what forced us to, we had built a data center that was designed for air cooling, and we thought it was going to be 25 years before we had to switch to liquid. That was our projections. The first GPUs came in, and they would not run at peak performance unless they were liquid cooled. And so it was actually less cost effective to run an air-cooled data center than to pay the entire full price to convert to liquid and also pay for the GPUs. So we ended up only spending 5 years air-cooled, and had to quickly convert the systems to be all liquid-cooled because of that. So this is NVIDIAnomics, they call it. This is Agam Shah, so Business Week magazine. It's fun to see what the business people think about this. But the claim, and there's a lot of people who dispute whether this can be sustained given the economics, but that the companies make $5 to $7 for every dollar they spend on the GPUs. And so if we look up here, the progression for the GPUs, we had the NVIDIA A100, the Ampere series was 250 watts power. Then the next generation was the H100, and that was 700 watts. The next generation after that, B300, is 2,500 watts of power. Now, these are peak power, but you can see the trend. All of this is because of wires, okay? This is all, and there's nothing, you know, we're cramming more transistors onto the chip. Each of these generations has a lot more transistors and is producing more performance. But the wires are the problem. And now the street price of these things are $30,000 to $60,000 per GPU for, you know, Vera Rubin. And they're making an 8x profit margin. So 800% profit margin is like, it's huge. I'm not sure if COTS is on our side anymore. You know, this is the 90s, we did switch to COTS, but you know, and despite the fact that these are $30,000 to $60,000 each, supply can't keep up with demand, and it's because they're making more money than the cost they put into buying the GPUs. And there's nothing to slow this wheel down except for the cost of power. We refer to this as the self-licking ice cream cone if you look at the economics with the circular lines. But this is what we're really facing right now. As a result, this is a chart by SRC from 2020 showing that at the current trend of power consumption, and they did a full model of the rate at which we're improving the energy efficiency of GPUs, which is to say not very well, that we're going to be a large fraction of the worldwide energy consumption in not too long. And the market dynamics is going to limit this, and it's going to put us consumers in competition with AI data centers. It is log scale, yeah. And I also gave him a hard time, so I finally found the guy who drew this chart. I was like, it looks hand-drawn. And he's like, no, no, no. And I was like, it looks fake. And he's like, okay, it was hand-drawn. But the slope was correct. And he told me the source, and it turned out the source was at Berkeley lab. I didn't know that. And so we had this, Sarah and Armand did the report for Congress. And this is actually how that slope was constructed, is from all of these studies from industry. And actually, he was right. The slope's correct, but it's definitely hand-drawn. But you know, you look at this and you're like, the energy apocalypse is coming. You know, this is where we're at. I like to attend the OCP Global Summit because the OCP and the data centers. The OCP, by the way, is just a supply chain management organ, and is really what it is. It's not a standards body even, but they create they create an engineering drawing of what they want, and they give it to all of their suppliers, and they copy it. So this is, and so you learn what the future is going to look like, because what the hyperscalers want is what the future is going to look like. And this is a 3,000 watt socket, dual phase cooling. Saw this this is a picture from 2024. And then here on the right was Google and Delta like the faucet company, collaboration on a 1 megawatt cooling distribution unit, liquid cooling. And I looked at it and just like the look on her face, it's ridiculous. Are you kidding me? And the very next year, suddenly computer conferences look like plumbing conventions. And so now there's 5 suppliers that have plug compatible. You can swap these, and so they have supply chain resiliency. Everybody copied the design. The guts are different, but those little pipes here, each one of these things within 1/10 of a millimeter are plug compatible. You can just swap them anytime you want. And I have to say, I hope there's no HPE people in the room, but going to this conference, every aspect of what you need except for the processor that's in the socket is standardized in such a way that there's 5 suppliers for everything. I think that, what do you call them, system integrators like HPE are obsolete. That's just from looking at that. Now let's look at, when we look at this from the other side, so the data centers are making $5 to $7 for every dollar they invest. We don't have that luxury in HPC. We have a fixed budget. And so if you look at this chart, this is the sum of all right, so we sum up the everything on the top 500 list. So if you see Eric Strohmeyer's charts, you got the top machine, you've got the bottom machine, and you got the sum of everybody in the list. And the sum is actually the smoothest number of them all. So we're projecting over time what's the rate of improvement in our LINPACK number for the sum of all machines in the list. Yeah. Yeah, China dropped out over here, and it doesn't seem to make a difference. Yeah. No, that's not true. I can tell you, I would not, that is not something that I would say about the machines. It would be nice if that were true. There's only one machine that's not optimized for LINPACK, and that's Fugaku. And that's only one. So we traditionally improve by 1,000x every 11 years, and we're now down to 5x every 11 years. And it's actually lower than that this year. I think it's 3x is the projection now. And this is despite our investments in exascale computing and all of that stuff. And LINPACK, everybody complains it's too easy a benchmark. It's all about the flops, and it doesn't emphasize memory bandwidth. And this is how we're performing on the too easy benchmark, right? So imagine what our performance is on real applications. So this is really what our future looks like if we continue doing what we're currently doing, which is double precision and all the way. And if we do leadership computing, we say, well, we'll just build a bigger machine. Well, scale just means more power and more capital cost. And the hyperscalers are already operating machines that are, order of magnitude larger in size than the leadership computing. I don't know if you can sell that to Congress anymore, that scale is the future. So we have to do something different. The National Academy of Sciences did a post-exascale study, and their conclusion was that they have to expand and create, where necessary, integrated teams that look at the key algorithmic and data access motifs for our apps, and then do collaborative hardware development that has a first principles approach that considers both alternative mathematical models in addition to pursuing alternative hardware models in order to address the limits of scaling. And this is really calling for a co-design that's much deeper than we're currently realizing. Yep. Oh, I think when they said motifs, they're saying, let's just look and see what kind of motifs we can recognize in the data. I don't know that they are really worth. I think the 7 dwarves or the 13 motifs kicked off a thought experiment, but I wouldn't say that they said that those are the 13. Yeah. All right, so this is a paper by Leiserson and Thompson. Leiserson invented the fat tree network. He's at CSAIL. Thompson's an interesting character because he has dual degrees in computer architecture and economics. And oh, yours, okay. I like, I go to his Future Tech meetings at MIT all the time, so he's fun. So, you know, the lesson that we learned from the 1990s was that you need to follow what the rest of industry is doing. It's not that you have to use a microprocessor. It's look at what the industry is doing, where the investments are happening, and you have to slipstream behind that. Leiserson and Thompson's thesis here is that we're moving from a transistor focus where you shrink the transistor and everything's better to a systems focus where you design the system around the problem you're trying to solve, and that becomes our new economic engine for microelectronics. And to do that, so the name of their paper is There's Plenty of Room at the Top. This is riffing on Feynman's There's Plenty of Room at the Bottom. Feynman was saying you shrink the transistor, everything gets better. They're saying, okay, we can't really get things better that fast anymore with shrinking the transistor. Now, at the top, you have to do software algorithms and hardware co-design together. And that's the missing piece, has been that we've kind of kept the mathematicians out of the room when we were designing stuff. This is no longer a feasible or practical way forward. You have to actually understand the math if you're going to design a better machine. They have some other papers that are really interesting about the economics of a post-Moore economy. But we need to pivot again, like we did in the 90s. But and so, you know, specialization is, it's not just the computer architect's go-to for improving performance of systems. It's also nature's way of extracting more performance when you have a resource-limited environment. So we used to have, you know, powerful general purpose processors when Dennard scaling was safe, so Xeon and the power. I apologize to my DOE colleagues who've seen this slide way too many times, but I figured there's at least one person in this room that hasn't. When we had post-Dennard scaling, when we couldn't scale the clock frequency anymore, we went to lightweight mini-core. In that era, we have Knights Landing, AMD, and GPUs to a certain extent, and this is represented by a couple of dozen really aggressive sparrows. But now we're in this kind of entering the post-Moore scarcity, and now the critters go after different food sources. They specialize, and they become like the Darwin's birds here. And this is exactly what Apple, Google, Amazon, and Microsoft are doing. They got the Google TPU. If you look at an Apple cell phone, it has, people have identified 50 or 60 discrete specialized accelerators, each of a different sort on it. In Microsoft, Amazon with its Graviton and Trainium, and Microsoft with its recent Mira system. So this is what the rest of industry is doing. We should be paying attention to what the rest of industry is doing, and we should figure out how we can slipstream behind what they're doing. And the Intel is not doing so well, in case you haven't noticed. So as one of our experiments here, you know, we use the Chisel language, which was developed in Berkeley campus, and we wanted to see how far you could push this. So we created, in a space of 6 months, we had about 3 engineers. I don't count myself because I'm a manager, I'm useless. But we had 3 people. We're able to crank out mixed radix in multi-dimensional, so it can do from 1 to 3 dimensions in any size FFT. It only took a few hundred lines of Chisel code to spec it out, and we were able to, so we did tape in at 16 nanometers. That's basically when you do the GDS to extract the power and area, but don't actually tape out because you don't have enough money. But we were able to outperform an NVIDIA H100 that was running the QFFT by a factor of 50 in terms of raw performance per area, and also 50x in terms of energy efficiency per flop. And those numbers were not achieved by the compute part of this. The numbers were achieved by optimizing the data paths, minimizing the data movement. Accelerators are no longer about the compute engine. It's really about minimizing unnecessary data movement. And so this shows, and so we can outperform, despite the fact that they're 10 times denser technology on the NVIDIA, and we're using an older technology, we can outperform. Imagine if we were on the leading edge. So this is kind of an existence proof that it's not impossible with more modern tools to do something that could have an impact. We want to generalize this approach, of course, to a spectrum of algorithms. But we don't want to just stop at the architecture and data path. I think that mixed precision arithmetic has to also be baked into this thing, and that's why I want to. So yeah, the secret sauce is the optimization of the data paths. So now I'm just going to say a few brief things about chiplets. People talk about them like there's some sort of magic going on. I just wanted to say that there is no magic. Chiplets are that you have a Moore's law for the number of transistors, but there's no Moore's law for the pins. The number of pins has stayed fairly static for a decade. So that means you have to drive each pin exponentially faster in order to get the data on and off the chip, and that costs you exponentially more power to do so. And it's gotten to the point, you saw that diagram, that it's at a crossover point, and that's bad. So chiplets is just the same as what we learned from parallel computing. They use an older process technology to engineer these, a lot of little micropins, these little solder microbumps. Now they have hybrid bonding. I'm not going to get into the details of that, but now you have thousands more pins per square millimeter, and they can operate at a slower data rate, but deliver petabytes per second of bandwidth. And then you use an older process technology to put the wires in the substrate here, and you can connect the boogers together. And now you don't have like that PCI bus thing. You've got minimized the communication distance, and you have modularity too. And so with the modularity, you have the opportunity to have 90% of what's on the chip is kind of boring stuff. PCIe, memory controllers, caches, and then you can isolate the stuff like that FFT chiplet that you want to contribute. And it's a much lower cost. I have a tinier chip that I'm making, but I get the bandwidth, almost the bandwidth of it being co-integrated, but I don't have to own the entire chip. I only have to own the little piece of accelerator that I have. And this is important because the hyperscalers, this is from the forcing function of the hyperscalers, are forcing our suppliers to open up their packages so that we can take a specialized chiplet and get it in there to get more performance and get specialization without having to own the entire chip, which is super expensive. We're talking about, you know, these reticle limited designs, but also the fact that the chip itself actually isn't that expensive. I hear people throwing numbers around like it's $1 billion or $200 million to create a chip. This is not true, and I'll show you in the next slide. The thing that's expensive that we cannot afford as a community is the platform. The platform is the software, the compilers, the operating system, even firmware, the people who make the motherboards, the people who do the cooling and bend the sheet metal. That ecosystem is something that we cannot recreate, we can't afford to recreate, and it's like 1 to 2 orders of magnitude more expensive than the chip itself. And so this is something that this is a door that was not open to us, that the hyperscalers, because they represent 55% of the worldwide microelectronics market, is controlled by the Open Compute Foundation. And think of that. And so if you're AMD and somebody who represents 55% of all server class microelectronics that shipped comes to your door and says, I want this, you're probably going to pay attention. But because they pried the door open doesn't mean it's closed to us. This goes back again that they're very open to other people coming in through the door, same door that they opened. So where I am in time. Okay, so let's speed up a little bit. So I wanted to go have a little vignette about posits. So I actually had a couple of whip-smart high school students that I had for the summer, but they became undergraduates at Berkeley, and we finished a paper with them. So Nick and Sanjana. And so we wanted to investigate the stability properties of posits. I don't think I can go through this. I think you guys are all probably familiar with the posits, but you know, rather than just having exponent bits, you have regime bits in addition to exponent bits. And the regime bits make it behave more or less like a logarithmic, more like a logarithmic data type than just a exponential. Yeah, this is more eye candy for posits. So if you visualize the precision, the tapering precision for a posit, if you imagine right here is like your baseline IEEE floating point, you have like this golden zone here where you have increased precision, and as you taper away from that, so +1 to -1, then it actually has reduced precision. So it's kind of robbing Peter to pay Paul a little bit here, but the claim from Gustafsson was that this is the zone we mostly operate in anyways, so that's the zone he's targeting. This is another view to look at precision across different formats. So we have float 64, you can see float 32, and then you can see the posit 32 here. Kind of, it's got that little bend in it there where it's got a little bit more precision and a little less on the outside. And then B float 16, it's a little bit more pronounced. Posit 16 to that. Now, just like the logarithmic data types, divide and multiply become a lot easier. But the flow chart for implementing subtract and add is crazy difficult, and it is also reflected in the resulting architecture. Implementing that, creating the hardware from that flow chart so add and subtract are hard now. Yeah, that's true. I would say that transistors are cheap, but every one of these branches that I take here requires an extra clock cycle. And so I have a really complicated pipelining challenge here. So the transistors are cheap. It's not about the transistors, it's about the microarchitecture. To meet timing, I have to have a lot of buffering in order to, a long flow chart requires a buffer between each of these stages. And a short flow chart doesn't require as much buffering. So meeting timing is a challenge. Somebody had a question. Okay. Now, in terms of scaling, if you have a posit, if you have a regular floating point number, there's no difference between this and this, the left matrix and the right matrix. But for a posit, there's a huge difference. The left matrix is a lot more better represented in terms of precision than the right-hand matrix. And so in our experiments, you'll see I'll have a chart on the left, which will be unscaled matrix, and the chart on the right will be rescaled to fit inside of that golden zone of 1 to -1, the Higgum rescaling. It's also the case that there's this inverse relation in terms of accuracy, solving linear systems based on the norm, which is kind of a representative of the condition number of the matrix. So we'll also sort the matrices from the matrix market according to their matrix norm, and just to make it easier to read off the data. So, if you look at conjugate gradient, so I had them, we created an emulation library, and they were taking the linear algebra course, so they implemented as they went through the class all of their linear algebra algorithms. And so you see here, it's kind of a wash whether the posit offers an advantage. If it goes below, then the posit does not offer an advantage. And if it goes above, it does offer an advantage. We see more of an advantage from the posits when you rescale them to be in that golden zone for CG. And this is, by the number of CG steps. If we look at Cholesky, it's a little bit better. So again, unscaled for good condition numbers, it looks a little bit better. Yeah.
Can you clarify what type of diagonal scaling you use? Because you scale both the rows and the columns?
Yeah. So basically, if you can get all the values of the matrix to be in between, 1 and -1, then in everything in between, the posits basically perform better. Is the central thing. In fact, I could probably skip ahead because that's going to be the central thesis here. So it's a kind of a wash. If you had a bad condition number, it's bad for the posits, and if you have a good condition number, it's good for the posits. Here we rescaled it all, and posits see an advantage over the floats. Now, I've heard Gustafsson say that a posit 32 is as good as a float 64. We've not seen evidence of that. And the digits of advantage. So, 1.2 digits of advantage is the best we were able to achieve. Decimal digits, yeah. In terms of now where we, yeah.
How do you measure those digits? We're talking about stochastic factorization here. What is the error?
The error is measured by digits of advantage in terms of decimal. When you print it out, convert it.
What type of error?
Root root mean square error. Huh? We wrote this paper in 2020. I mean, it's in terms of the residual error, I don't. Yeah, this is the residual error. I'm sorry. Yeah, this is the residual because this is Cholesky. Yeah. Now, we see when we did the mixed precision, 16 plus 64-bit, you see a more pronounced advantage for using posits. So posit 16 had a more pronounced benefit when you get in that golden zone than the posit 32, and so now we're starting to see something more interesting. Yeah, so here's the mixed precision. But anyways, so let's go. Posits can squeeze a little bit of extra numerical precision out of floating point bits if you rescale the problem to fit into that optimal range. And that's because of that taper that I showed you. And mixed precision might be a good place for posits to play because we didn't see as much of an advantage for the 32-bit precision. But the other observation is one thing that we pitched out early. So we had Gustafsson's mathematical notebook, and we're like, why does he not convert into a binary representation when he does summations? And Gustafsson explained that that's the quire. So whenever you do a summation, it doesn't do any round off. So infinite summation, no round off. And now Mathematica allows you to do that. Normal accumulation register would not allow you to do that, but he said it's a quire. And so we refer to this as rounding deferred summation. So we've started to look in, and so we said, well, we're going to pitch out the quire. We're not going to allow it. We're going to only measure the benefit of your numerical format. Yeah?
Is it the same as Kulish accumulator, just accumulate longer?
Yeah, exactly. Yeah, so we'll talk about that in a sec. So he invokes the quire, but we're like, but the quire could also benefit IEEE floating point arithmetic. So we thought it was kind of an unfair comparison to have the quire for the posits and not have it for IEEE. So we conducted all of our tests without allowing a quire, and so it was marginally good. And it's also, when you compress into the optimal range, we're leaving a lot of representation space unused. So maybe there's even more advantage if you do some numerical analysis. So rounding deferred summation, also known as a quire, in posits. It's not a new thing. As Jim pointed out, Kulish and accumulators. But if we just lay out a floating point number is basically a compression of a very large integer. And so if you think in terms of, the size of integer you need to represent the entire representational space is 1 times the size of the mantissa and 2 to the exponent size. And you can look in this table here. For FP64, you need a 2101-bit integer register to represent the entire state space. And if for FP16, you can do it in a single 64-bit register, it's 43 bits. But the way you decompress from the floating point into this integer is that you take the mantissa and you use the exponent to show how many bits you have to offset into that integer register to deposit or accumulate that, that mantissa into whatever you're accumulating in that register. And when you do so, you have no round off. Every time you accumulate, you could overflow, but you will never have a round off when you're doing a long integer summation. And also, whenever I hear applications, people say they can't tolerate lossy compression. It's like you're using it every day of the week, dude. So yeah, slap them if they say that they can't. This floating point is well-characterized lossy compression. In terms of, this is a paper we did with Sherry Lee and David Bailey a while ago. So to give you an idea, the rounding deferred summation We do longer and longer and longer, series of accumulations, and there's no rounding error. Whereas even with double double and long double and double, you can have some accumulated rounding error over as these sums get longer. So here's the effect of the rounding deferred summation in terms of CG cycles. We're working on comparing this against different flavors of stochastic rounding. So we're updating the emulator for this. And, there's, you can see that there's more of an effect from implementing the rounding deferred summation to improve the CG performance. This one's particularly big here. For bfloat 16, it can be a huge benefit to conjugate gradient, yeah.
One question about that. So if you take that matrix and you use whatever bfloat 16
Yeah.
to implement your CG,
Mm-hmm.
then you're reading in the matrix values from file, and
Yeah.
they convert them to bfloat 16.
Yeah.
But then you're solving a different problem than if you read in the values.
Yeah, we're solving a problem. It's
It's a different
yeah, it's a different problem. Yeah. All right.
So it could be that using the bfloat representation of the values,
Mhm.
the system the condition number is much worse. So
Okay.
it could be that
We'll have to recompute the condition number then under bfloat 16, and to be fair, I guess, to these. So when you convert to bfloat, what would you recommend? Would you recommend rescaling as we read it in before we pop it into the bfloat 16, or what's the?
I think it's very difficult to actually make a comparison across these different, because basically you have a problem at hand.
Yeah.
And you cannot just tell your customer, hey, I'm solving a different problem. It's much faster, but
So we'll talk offline about how I can make it so that we're solving the same problem. Yeah.
Here, the two colors are fair, right? In both cases, the matrix is using bfloat 16, right?
Yeah.
but across the different categories, it's difficult to compare.
All right.
Take the matrix in lowest precision. Right. Yeah, you would need a matrix that
Starts at the low precision. Okay. All right. That's an interesting thought. All right. Yeah, I think, the across is probably not as important as the within. So double is fairly consistently the same performance, and it's not really directly comparable, I guess, across these different formats. But you can see within a category, you see a more pronounced effect for bfloat 16 than for 64-bit. Yeah.
How important is it that the summation is actually exact? Wouldn't it be enough to say accumulate the net?
That's why we're going to experiment with the stochastic rounding as well. Yeah.
One question: which terminating condition is used for GG?
I can't. That's a good question. For this particular one, we select a termination condition. It's like 10 to the -7, but I don't. And some of these, so we need to work on this because some of the matrices never terminate. Yeah.
For instance, I noticed in my research, maybe not my research, but the default often is a dependency on the machine epsilon.
Yeah, that's right.
Implementations like composites, they have a lower machine epsilon because they take the best case, which means that they have a harder time because they need more iterations.
Yeah. Yeah. And the answer is it's 10 to the minus something, but I don't remember specifically for this one. And
Right choice.
yeah. So anyways, rounding deferred summation for CG but we're going to extend this to Cholesky, LU, FFT. So it seems that the summations are more implicated in the performance benefits of posits than the representation itself. Having lossless accumulation definitely helps, but we can look at some intermediate cases as well. And we think that the logic for the integer accumulation ALU actually is relatively simple in comparison to a floating point unit. All right, so let's talk a short vignette about hierarchical methods for my AMR friends. So, we have, let's see here, I have to click on something here. There we go. So we're looking at advection with a specified velocity field. The benefit here is that, perhaps I can tie my refinement of my precision my numerical type to also the spatial refinement and also time refinement, that when you go to the finer grained levels of a AMR problem, some preliminary experiments here. If you do this solution in double precision, you can see clearly there's a lot of artifacts and stuff for the single precision case. But actually, what you do, I can't see the refinement boxes. There's little refinement boxes here, but so if we actually have the coarser grids done in 32-bit precision or lower precision, you do have artifacts here, but they're not interesting. It's not where the action is. And what Anne is showing here is that we can actually preserve the important part of the problem solution because we're doing double on the refined parts. And it really, quite frankly, doesn't matter that we have artifacts in the part where the solution is not as high quality. Yeah.
And just to make sure I understand, the refined parts are a finer mesh, so
They're finer mesh.
several times more work there at the higher.
Correct. Yeah. There's several times more work, but you have fewer. You have a smaller part of the computational domain. So the fastest and most energy efficient flop that you do is the one that you don't do. That's AMR in a nutshell. So we're starting to see what's the quality of the solution we can achieve with different numerical precision at the lower levels of an AMR hierarchy. So short thing about ALU complexity. I think you've already seen this, but we'll just go through it again. We've seen Patterson's chart here, but it's an exponential scale, so we can look here at how much is the ALU actually contributing to the power consumption. And the ALU's consuming is a very small fraction when it's 64-bit, or no, this is 32-bit, sorry. And if we make it go to 0 by going to 4-bit precision, I don't know, it's just not a lot of difference, yeah.
So doesn't that picture depend on how much data we use?
Yeah, that's right. It does depend on how much data use you have on average. But anyways, if we're going to go with the lower precision ALU, so this thing though, I'm really talking about adding features to the lower precision ALU and not adding features to the high precision ALU. This one, data reuse, it'll be noticeable. For this one, we could have 1,000, so it's 0.07 picojoules in comparison to a total of 50. You'd have a whole lot of data reuse, and the extra complexity isn't going to impact. Yeah. This is the breakdown. Yeah, the absolute value though only differs by the 1.31 if you do double single precision, and here 0.007. Yeah, that's one part. That's one problem with the Patterson chart. I realized after I created the spreadsheet, I need to go talk to Dave about this. I acquired these slides when I saw Kathy present them, and I sent an email to Dave. Hey, can you send me that slide? And I got the slide and didn't really interpret it too much. Now that I've done the spreadsheet, yeah, you're right. We need to work on this. But again, it's probably not. It'll probably be proportionally smaller when you're moving less data, because again, the data movement dominates. The ALU is really, 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 really tiny.
So the numbers you have on the pie chart,
Yeah.
I presume are picojoules.
Yeah.
So it's, in that sense, the 31 picojoules is fetching data from HBM.
Yeah. So I should have divided these numbers by a factor of 16, I guess. But still, the ALU would still have been a small part, but I need to go back into the spreadsheet and redo this.
Yeah, but then the other part of it is, again, going back to Jim's point of that, how many times you use the
Yeah.
data, because if you want to get peak performance out of your GPU or whatever processor you're using,
Mm.
you need an arithmetic intensity around 700.
Yeah.
So, take your ALU number, multiply by 700, and see what
I have a spreadsheet model. We're going to go back in, we're going to fix this, and then experiment with different reuse numbers, and see how this plays out if we have different amounts of reuse. I don't know if I can achieve 700 average reuse. I haven't seen that in many. Well, with gem, but yeah, I mean, with gem, if it's a really big gem, if it's the size gems that we typically do, I don't think so.
If you're emulating a high-precision gem with low-precision arithmetic,
Yeah.
computational intensity goes up a lot.
Oh, really? Okay. Well, let's enter new numbers into the spreadsheet and see how this plays out. So we wanted to see also how much area these things consume, and we don't have direct access to their IP, so we have a floating point hardware generator called OpenFloat, and what we did was generated candidate FPUs for FP4 through FP64, and made sure that we had enough pipeline stages to meet timing at 2 gigahertz at 7 nanometers. And that's trying to duplicate what they have in the B200. The assumption is that if we can meet timing at 7 nanometers, it'll still meet timing at 4. We don't have access to a 4 nanometer PDK. So we adjusted, we projected forward what the area is when you shrink it. So going from 7 to 4, you're shrinking it by about half. And we wanted to see the relative area. So this is the floating point rate for B200 for the different categories of floating point numbers it handles. This is the area per ALU, and you can see that a double precision ALU consumes a lot of area in comparison to the 32, the 16, and the 4. But when you actually do the relative total area given the number of these units that they have on the chip surface, you can see that the 4-bit actually is dominating the consumption of surface area in the chip. But then you put it all together for the total chip area, which is 1,600 square millimeters. All of these put together, assuming there's no reuse or no sharing of resources between these ALUs, is still not the dominant factor. All right, so we'll continue, and I'll put the pedal to the metal here. Not much left, actually. So flexible hardware helps de-risk. This is the thing I was telling you about. AMD's hardware can support any number of mantissa versus exponent bits. It does it in each of the bins, though, so like 8, 16, and 6, for example. So it's not fully general purpose in terms of that. It's for each of the bins of width. And MXFP4. Why do they do this? Because they're worried that 3 months before product launch, NVIDIA will say, we have this new format and everybody wants it, and AMD doesn't. So it's all in there, and all they have to do is enable it in their compiler by giving it a name, and then it becomes a data type in the compiler. So why don't they just expose this whole variable thing? And the answer is nobody wants to qualify a compiler for every possible combination of mantissa and exponent. That's why they won't give it to you. So this enables them to write at product launch. They can rewrite the back end of the front end of the compiler to recognize that type and program it correctly. So that's how desperate they are when it comes to low precision. That's how important low and mixed precision is to a company like AMD and probably NVIDIA too. So, this is where we get to, so what can we do with a more complex ALU? We got stochastic rounding. There's many flavors. I'd like to conduct some experiments with the emulator to say which flavors are better than other flavors. Same with rounding deferred summation. Maybe we don't, like Jim was saying, maybe double's enough. I don't know. Gaussian data types. So this is an even crazier. Oh yeah, if you do rounding deferred summation, so this is the Higgim diagram. You'd be basically flat, across. But anyways. The other thing is Gaussian data types. We used to, when we were in lead up to the exascale program, we talked about this a lot. UQ, so uncertainty quantification, the state of the art is you do an ensemble of runs and you perturb the data between each of the runs to get a sense of what the average behavior is and where there's a lot of divergence, where I always hate to say Lyapunov exponent because I can't pronounce it correctly, but anyways, if you see a lot of divergence and you have a lot of uncertainty, but you have to run thousands of runs and stuff's got to run through memory many times, the notion of Gaussian data types was to invert the UQ cycle, where every scalar in the code is represented as a Gaussian splat. Now you have to reset the Gaussian each iteration, but because they just spread out. Entropy is entropy, but you can use the accumulated the change in the sigma of the Gaussian data type, and this is something that you can achieve a lot of compression, where you can use two low precision floats to represent the sigmas in each of the dimensions, and when you get it into the ALU, you can expand it out into a matrix of values, compute on that matrix of values, see what the new sigma is, and compress it. Now, it's pointed out that the meaning of multiplying two Gaussians together is very different than the meaning of adding two Gaussians together. They will not necessarily be a Gaussian, but it turns out the UQ people don't care either. And when they do the macro scale UQ, they average things out and they say it's kind of like this kind of Gaussian. So if they do it for the regular way they do UQ, I think it'll be okay if we do it for the inverse UQ. That's a guess. So there's other ways to, this is the last piece, other ways to reduce data movement distance. So reducing data type widths is one way. And also, I would hope you got the lesson that the ALU doesn't necessarily have to operate at the data width of the operands that came in. It's an incremental cost more to make it wider and more accurate, but it isn't a deal killer to do that. But it isn't the only approach. There's other techniques that are naturally composable with reduced precision that you should also consider. So take, for instance, AI has data and model parallelism. Well, we know data parallelism. That's, when we do ensembles, we have that. Model parallelism has tensor parallelism. It's more like our domain decomposition. And then pipeline parallelism, which we don't do because it's hard. But you could do it. If you look at the generative AI and large language models, they already expose simultaneously in these NVL72 clusters, 3 different dimensions of parallelism. If you go to the NVIDIA PyTorch page, there's actually, they've identified 5 different forms of parallelism. We typically only exploit one of them, which is domain decomposition. But they've identified 5 other dimensions of parallelism that we do not use. And these dimensions of parallelism actually map very well also to the kind of hardware accelerators that my group's been experimenting with. So take, for example, on the left here, you got your von Neumann processor. Stuff goes in, out, back in, back out. When you do data flow, which is what we need for circuit design, you're just stamping out the ALUs onto the chip and the data flows through, and you're implicitly kind of trying to minimize the distance between the ALUs. And you get a lot of reuse from the pipeline dimension, which is something we don't typically exploit with MPI. And you look on here on the left too, the languages that we use to express computation are inherently oriented towards a instruction processor, where even if it's parallel, I'm doing this, followed by this, followed by this on each processor in the system. So the left-hand side lends ourselves to having highly tuned libraries where I invoke the FFT and then I invoke the gem. I do this sequentially, and each time I run the data through the processor and back out again. This is encapsulation. This is how libraries work. But if I am doing it as a circuit design, I actually have to set things up so I flow blocks of information between these ALUs, and then I don't go take a round trip back to memory between each of these optimized cores or function blocks. And so if you look at this, this is for our experiments with VASP, so density functional theory, which is a really important code for material science. It's 1/3 of all HPC workloads. If I do VASP kernels. This is the central kernel, the self-consistency kernel. The blue is the amount of time that I spend in loading data from memory. And the orange, or the yellow here, is the amount of time I spend in the ALUs. But if I go from this way of invoking the optimized libraries to this pipeline parallelism, as I collapse the stages here, so I'm merging stages of computation like this, now I can be back in the zone where I'm bounded by the memory, by the ALU, sorry, and not by the memory bandwidth. Again, this is such a difficult way of exploiting a dimension of parallelism. It's so difficult to exploit, we typically do not do it. I know that Torsten Hofler's group is trying to create a compiler that does this, and it turns out to be hard, but at least somebody's working on it. And so this is, we actually emulated that kind of pipeline on a conventional microprocessor, and even without custom hardware, we're seeing a 10 to 12x boost in performance for VASP by taking the kernel stages and having one processor do the FFTs and another core do the DGEMs and another core do the TSQR and so on and so forth. Even though there's a lot of mismatch in performance between the stages of the pipeline they do, the benefit in terms of reducing memory movement, data movement, is enormous. And if you combine this together with reduced precision, it would be massive. We're talking, now we go from 1 order of magnitude to 3 orders of magnitude. Now, one problem with this is that this, going from the left to the right case, we've broken encapsulation, so we can't hide stuff in libraries anymore. So that's a challenge, and that's what Torsten's group's trying to fix. And the second is that this right-hand model is completely antithetical to GPU kernel launch and offload. Offload is completely the wrong model. GPUs cannot do this, and that's a problem. Yeah, so we didn't take into account NUMA nodes. So in this case, we're using an older school GPU, an A100, which is a single die, so there's no NUMA. And we tried to do it in the GPUs. I didn't show that result because it just didn't provide a gain. For the AMD processor, we had a single socket system, so I don't know. I assume, though, the cut set through a NUMA node would probably be better because we're bouncing this off of the last level cache, which isn't really that fast, and we got that 10x benefit bouncing off of LL3, the L3 cache, and that's not a fast cache. If we could have buffering that was operating at L1 cache speeds, then we would get even bigger benefit than what you're seeing here. I'm going to skip the wilder thoughts because it says John goes one step too far and embarrasses himself in front of a room full of numerical analysts. If I haven't done so already, by the way, but we'll just go to the conclusion. Data movement dominates. Narrow data types reduce data movement. I was thinking I'd just start with that and then drop the mic. From a computer architect's perspective, yes, absolutely. Fewer bits means less energy and less space. Alternative data representations thus far offer marginal benefits. We'd like to see more value in techniques like RDS and stochastic rounding, and also hierarchical representations like AMR and multigrid. FPU complexity grows quadratically with FP bit width, but the FPU itself is so inconsequential compared to the data movement part. In terms of power and area, I still maintain it hardly matters, but we'll continue to mess with that spreadsheet to see if that intuition plays out under different data reuse and other assumptions. And there's more to reducing data movement than just a narrower type width. And so that's my pessimism part, is that this is a good solution, but we have to pull out all the stops and look at all the solutions that reduce data movement. And there's a lot of other techniques. This is one really good technique, but there's other stuff that we can combine with it. And these are composable techniques. So let's look at it. So that's it. Yeah.
So just make sure I understand the point, but where you make the FPU such a minuscule cost, then why are people abandoning FP64?
No, that's not really it. They're banding FP. So the explanation, like I said, Ian Carlin, when he was at NVIDIA, he was responsible for doing all the procurement benchmarks. So DOE has like 30-some procurement benchmarks, and we use this to select machines. Ian basically sat down and went through all those benchmarks and said, if I have 40 teraflops on the B200, then I have enough that adding more floating point 64 units will not improve my performance enough to make a difference in the procurement. So they stop. And so that's a market research-driven decision. I don't think you should have more FPUs than you can use. And so I think Ian's phenomenologically looking at what we say are important in our workload has arrived at the correct number of double precision floating point units to serve our needs. We gave them 32 applications. That's what they say, for sure. Yeah.
So we often do arithmetic in the same floating point format that we move data around in.
Mhm.
But of course, the old Intel FPUs had
80 bits, yeah.
So, is there any rationale to keeping around some additional precision?
No, I think it's a good thing. It confounds numerical analysts such as yourself, but yeah, I think that's one of the things I'm advocating for. I haven't run the experiment yet with the stochastic rounding, but I suspect that if the internal data representation has more bits in it when you're doing the ALU, then you're going to actually write out or read in or write out that you could, be more accurate in terms of the rounding direction when you do the stochastic rounding. So apparently flipping a coin 50-50, which is what you get if your internal to the ALU representation for the number is the same as the operands, the best you can do is 50-50 because you have the internal to the ALU, there's no additional bits to tell you whether I should bias towards round up or round down. It's not in the ALU unless the ALU has more bits in its internal representation than you're going to actually ultimately output.
Let me sharpen the question.
Yeah.
Independent of stochastic rounding,
Yeah.
is the Intel you actually had 8-bit registers, right?
Yeah. True.
Is the wire cost of moving data around that you were talking about so extreme that nobody wants to put in registers
Yeah.
close to the thing?
Yeah.
Or
The registers are more costly than if you did it in a kind of that data flow fashion. So if you could chain together arithmetic operations. So our research plan is to say how much do you get if you have a wider internal representation, but we don't do anything with the operands that go in and out. Will we make stochastic rounding sufficiently better that it's worth it? Then the next layer out is let's widen the registers from the FPU and see is that beneficial to have a chain of operations when they're resident in the registers? Is that even better than that? And we're just going to try to see how far out before the energy cost of moving the data confounds the benefit that we achieve from the higher resolution. Yeah, Jim?
So to make sure we're talking about the same kind of stochastic rounding.
Yeah.
Because the 3109 standard has 3 kinds and our simulator has 5 kinds.
Yeah.
There's just a lot of them out there in the literature.
Sure.
In addition to that, there's also another parameter, which is how many random bits you use.
Mm-hmm.
And if you want a lot of random bits, that sounds more expensive than just doing the floating point operation with more bits in the first place. So what are
We have people who can write hardware and write it very quickly. We'll find out how much those extra bits cost you.
So how are they generated?
How or what generated?
Random bits.
I mean, I maintain I can't think as a hardware architect how you would be able to utilize those extra bits without the ALU having a wider data representation internal to the ALU than the baseline.
Yeah, because you have to add those random bits to the trailing bits and then.
Yeah, in addition to having to randomize, but being able to, you have to have more information in order to bias the stochasticity towards the round up and the round down. And if you have a 16-bit format and internal to the ALU at 16 bits, then the best you can do is coin flip. We want to do better than a coin flip, but we want to see if there's a benefit to being better than a coin flip. Yeah.
Suppose that one argument in favor of stochastic rounding would be that, sure, you have the internal data with 32 bits, so why would you round it? But maybe you want to put the data in 16 bits for storage reasons.
Mm-hmm. Yeah, that's kind of what we're talking about, is that the ALU can be wider internally, and I use that extra information to make a more informed choice for my stochastic rounding, whether I round up or round down. How beneficial is it? I don't know yet. Hadn't run the experiment. But yes, that's kind of the discussion. Then the output will be back to 16 bits, but it will have made a more informed choice about which way to round. Yeah, Peter?
So you mentioned that the decrease cannot do the data flow. So how would you characterize the inner graph, total graph, and OpenMP graph extension?
Yeah, they look terrible. Yeah. Yeah, sorry. The graph, the tasking extensions to OpenMP is where the OpenMP standards people departed from what, used to be. The whole idea with OpenMP is that if you ignored what was in the comments, that it would still execute correctly. And their tasking directives is where they departed from that, where if you do not interpret what's inside of the comments, then it will not execute correctly. And I don't know, that's kind of challenging to wrap my mind around. I really miss when OpenMP fit in a single index card. And same with MPI. Oh, yeah. Okay. Oh, yeah. All right, thanks.
Is this yours or is it from?
That's from them, yeah.